Okay, welcome back, everybody. The end of yesterday's lecture, um, I hinted that we were about to take a slight detour. It's not even really a detour, right? This is, as we'll see, this is exactly um, where a lot of the motivation for this stuff comes from. But a slight detour into linear algebra. So quick refresher from linear algebra. So we'll think about vector space V, right? So what makes the set a vector space, right? It is, hold on, cats are fussing at each other. So what makes a set V a vector space? Remember, it satisfies the vector space axioms. I'm not going to write all of those, but the easiest way to remember them is it makes the operations on vectors, so vector sum and scalar multiplication, behave the way that it does in Rn, right? So there's vector space axioms that tell you how the operations of, say, uh, you know, vector sum works and scalar multiplication of vectors works, where C is some scalar. Of course, we can talk about complex vector spaces, whatever, where your scalars are in C instead of R. Doesn't matter. Um, but we'll just say these are real vector spaces. Okay. And so, for what we want to talk about, some things to remember, right? There were uh, kind of a few important bits. So a vector space satisfies these vector space axioms. That's what made it a vector space. So it had these operations of vector sum and scalar multiplication defined in the usual way, right? So to sum two vectors, you just sum their components, right? So in each slot, you sum the corresponding components. Scalar multiplication, you know how that works. Um, Now, the thing to remember was that there were finite dimensional vector spaces, right? Finite dimensional vector spaces versus infinite dimensional vector spaces. So infinite dimensional vector spaces were probably treated as more of like a curiosity in your linear algebra course. They basically existed as a source for counterexamples. What do I mean by that? It turns out that most of the stuff you did in 240, while a lot of those computations would work in a corresponding infinite dimensional vector space, most of the stuff assumed that you were in a finite dimensional vector space. And when you're in a finite dimensional vector space, one of the facts was that, well, in a finite dimensional vector space, V is isomorphic to some Rn, right? So a finite dimensional vector space behaves exactly like some Rn, right? So if you know how vectors behave in Rn, then you understand how it behaves in a finite dimensional vector space. Okay. So first of all, what does this even mean, finite dimensional? Well, every vector space has a basis, all right? You don't have to ponder that too much, right? That may or may not be equivalent to like the axiom of choice or one of these things. Um, what is a basis? So a basis for a vector space is a set of linearly independent vectors that span the vector space. So linearly independent and span. Now, combining these, it means, so the fact that they span the vector space means any vector in the vector space can be written as a linear combination of the basis vectors. The fact that they're linearly independent is some statement about, this is like a vector equation statement that forces this set to be like the most efficient spanning set, right? So most efficient spanning set. So they span the vector space, and also they are the most efficient thing that does that. Hold on for 1 second. I have my car is in the shop, so I'm getting a call from the mechanic. I'll be right back. Okay, I'm back. Oh man, they said they were fixing it for free. That's like winning the lottery. What is going on? That's exactly what you want to hear. Okay, anyway, so a basis is like the most efficient spanning set. So it means that any other spanning set, right, either has the same number of vectors or more. It can't have less. And of course, this basis is exactly what's used to define the notion of dimension in the first place, right? So the dimension of a vector space is just the number of basis vectors in any basis for the vector space. Okay, and so there are these theorems from linear algebra that tell you that the if you have two different bases for a vector space, then they have to have the same number of vectors, right? So whatever number that is, they have to have the same. So one can't have more or less than the other. Two bases have exactly the same number. That number, which is going to be fixed among any basis, that's why it doesn't matter what basis you use to do this, that number is the dimension. So if that number is finite, right, that's a finite dimensional vector space. If you have a vector space for which there is no finite such set, that's an infinite dimensional vector space. So if finite dimensional vector spaces can be thought of as, since they are just isomorphic to like Rn, what are examples of infinite dimensional vector spaces? Well, how about like the space of all smooth functions on R? Or maybe just the space of all like C1 functions on R. So their first differentiable functions on R. The space of all integral functions on R, or on some set we'll call omega, right? So thinking of these infinite dimensional vector spaces as function spaces, well, not just thinking of them in this way, but let's suppose I give you the examples, like any of these three examples. It can be shown that each of these are in fact vector spaces. The vector sum operation is going to be a pointwise sum of functions, right? So like f plus g, right? Pointwise sum of functions. These functions are going to be my vectors, right? And they're going to behave just like vectors. The only difference is if vectors in Rn have n components, right? Finitely many components. These functional vectors have infinitely many components, right? And you could think of the variable used, right? So if I write f of x, you could think about this as being like the xth component of f. So it's almost like that value, like this variable value here is like the index of this infinite vector. Okay? And there's a like one-to-one analogy here. Vector sum is going to be pointwise addition of functions. Scalar multiplication is going to be scalar, pointwise scalar multiplication of functions. Okay. And so, what do we say? Linear combination, right? So just recall a linear combination is just a sum. So I have scalars, c1 x1 plus c2 x2, or these are vectors. I put the vector bar over them. Some people use hat. That's fine too. So it looks like this. If, say, we'll say that the x of I are, so if the x1, x2 out to xn form a basis for a vector space, we'll call it V, right? Then any vector, say V, in V, can be written as a linear combination of the basis vectors. Now, this is true of any basis. This is also true of any spanning set. But again, as I said, a basis, remember, is like the most efficient spanning set. And this is nice for a variety of reasons. Okay, so if you have a basis, then that's what you want to use. Of course, you might remember from linear algebra, not every basis is created equal. Some bases are better than others for a variety of purposes. And so there was a way to change bases, right? You could, if you just had another basis, you could just use that basis. But if you had two different computations with respect to two different bases, then you could apply a change of basis transformation, right? This is all the kind of stuff you did in 240. So any vector V can be written as a linear combination of the basis vectors, i.e. there exists scalars C sub I in R such that this vector V can be written as C1 x1 plus C2 x2 and so on out to Cn xn. Okay, a quick way of writing this, of course, is just to write this as a sum from like I equals 1 to big N of C sub I x sub I. Right? Okay. Now, of course, there was some other things we could talk about. So there was additional structure on our vector space. Let's restrict ourselves to finite dimensions first. So this was something that is an additional structure. It's something that does not just come to the vector space like on its own. You put it on the vector space. You can think of it like that. So additional structure on the vector space, an inner product In the example you're probably most familiar with, this is the dot product. So if I have two vectors, x and y, and I dot them together, we'll say each of these have the usual notation in our finite dimensional vector space. We'll say the dimension is big N. What is this? This is just x1, y1 plus x2, y2, and so on out to x in yn, where these aren't vectors. Maybe it's a little bit confusing here, but when I want something to be a vector, I have a bar over it here. These are components of these two vectors. So the vector x has components x1 to xn. The vector y has components y1 to yn. And their dot product looks like this. Of course, you write it in shorthand with sigma. So this is sum from I equals 1 to n of x sub I, y sub I. There we go. Okay. So this dot product gives us additional structure, right? What did this additional structure allow us to do? So geometrically, what is the dot product giving us? This gives us both length and angle associated to vectors. So geometrically, like, this is the thing, right? This basically gives you everything. If you're thinking of, like high school type Euclidean geometry that you're doing in the plane, for instance, right, in R2, this literally gives you everything you care about, right? Length and angle, that is exactly what you care about in geometry, and this, both length and angle, get spat out of the dot product, right? How so? Well, recall, right, that a length, it's like the length of the vector x. I'll use double bars here, just from linear algebra land. Of course, in this course, in the textbook, mostly uses absolute value here. I'm going to use double bars here to stress this, just because I'm about to use double bars when we talk about functions, and I want the analogy to be like as clear as possible here. So the length of a vector, right, was actually, you could define it, if you like, to be the square root of that vector dotted with itself. Right? So this is the square root of x1 squared plus x2 squared, and so on, right? Okay, or another way of writing this, of course, an equivalent way, is to say that the length of a vector squared is that vector dotted with itself. Okay, so whatever way you want to think about it, right? Here it is. So this is how length of a vector and the dot product are related. What about angle, right? Well, we know our cosine formula, right? So the cosine of theta, if theta is the angle between, say, x and y, so let theta be angle between x and y, then cosine of theta is what? It is the dot product of those two angles divided by the product of their lengths. So you might remember this from either Calc 3 or from 240, right? There's your cosine formula. Okay. So here is exactly how the dot product is related to length and angle. This allows us to project, so orthogonal, we'll call it, projection of a vector x onto y, we'll say. So the way that we write that, you might remember this expression. This is the projection of x onto y. It can be shown that, so if I draw a picture of what is going on in, say, R2, if this is the vector x, and this is the vector y. Orthogonal projection was thought of orthogonally, and we'll talk about that in a second. Shining flashlight, say, from the positive upper direction here, straight down, this casts shadow, right, onto the vector y. And I want to write a vector that is a scalar multiple of y. It is parallel to y, that comes from x in some way, and that's exactly this projection vector. And of course, we can talk about, if you took 240 or Math 461, in either of those courses, you talk not only about orthogonal projection onto a vector. This is a special case of orthogonal projection onto a linear subspace. There's, orthogonal projection onto more general subspaces, right? This is what you had a big theorem, orthogonal decomposition theorem, right? There's all kinds of this stuff that you did in linear algebra. But anyway, the projection of vector x onto y was given by, this was x dotted with y over the length of y squared, so y dotted with itself, times y. Now, one way to look at this is just some scalar here times y. I knew that it would be that because it has to be parallel to y, so it's got to be a scalar multiple of y. And this is exactly the scalar in question that does this, okay? All right, but since the dot product tells us about the angle between vectors, immediately from this formula, x and y are perpendicular, or what we'll more likely call it orthogonal. Well, that is, they have angle between them pi over 2. Cosine pi over 2 is 0, so, and of course this denominator is not going to be 0 for non-zero vectors. So if and only if their dot product is 0. So this gives us a notion of orthogonality, right? Okay. So now this lets us say, well, an orthogonal basis of a vector space V is a basis of V which is pairwise orthogonal. What does that mean? It means that I have a set, we'll call them x sub i's here, so this is x1 to xn, and x sub I dotted with x sub j is equal to 0 if I and j are different. So this is just to make sure, because we don't want to talk about, like, we don't want to talk about having a basis where, you dot a vector with itself and get 0. Obviously, that's a 0 vector. That's no good. So that's, that's not going to be included. So this is the only kind of requirement like this that we could possibly have. All right, so there it is. So this is the notion of an orthogonal basis. An orthonormal basis is an orthogonal basis where each vector is a unit vector, so it has length 1. So this is even nicer because not only is it orthogonal, but also the lengths of the vectors themselves are all 1. Okay. Now, why is an orthogonal basis so nice? So first of all, we already know an example of an orthogonal basis. So the standard basis of Rn So this is my set of vectors E sub I, where I is between 1 and n, forms an orthonormal basis of Rn. Right? We know exactly what these look like, right? So E sub 1 is the vector 1, 0, 0, and so on up to 0. And E sub 2 is the vector 0, 1, 0, all the way out to 0, and so on. And of course, writing a vector with coordinates, right, relative to the standard basis is super simple, right? That's what we do all the time, right? That's basically all we do outside of linear algebra. We're very happy to use the standard basis whenever we can. But why is an orthogonal basis nice to begin with? Right? Why is an orthogonal basis nice? So here's a question. So why is an orthogonal basis nice? The answer is, I don't know if this theorem usually has a name in linear algebra, but basically it is very easy to compute the coefficients in any linear combination of the vectors in an orthogonal basis. In fact, let let's say x1 to xn be an orthogonal basis of V. Okay. Let V be any vector in V. Then V can be written as a linear combination of these orthogonal basis vectors, where the scalars in the linear combination, the x sub i's, the scalars in the linear combination can be exactly written as, so this is V dotted with x sub I over x sub I dotted with itself, right, times x sub I. And so, of course, x sub I dotted with itself, this is just the length of x sub I squared. So, in a sense, what is it that's going on here? These coefficients, right, are exactly the ones from the projection. Right, I can rewrite this. Oh, picked up the wrong pen. This is the sum from I equals 1 to n of V dotted with x sub I over the length of x sub I squared times x sub I. So this is exactly the expression in the projection. So this is saying that for an orthogonal basis, if I write a vector as a linear combination of those, the scalars are the same scalars that come from the projection, meaning that I can write any vector as a sum of these orthogonal projections in this way. Okay. This is really, really nice because normally what would you have to do here, right? Recall your 241, 461, or sorry, 240 or 461 material. What you would have to do is you would have to solve a system to find these scalars, right? These c sub i's. This is a vector equation. To solve this vector equation, you would have to solve a matrix equation. That's what you have to do in general to find how to write a vector as a linear combination of, say, given basis vectors. But this is saying that For an orthogonal basis, these scalars can be computed automatically, instantly in terms of dot products. No need to solve matrix equations or anything like that. So this is super duper nice. Okay. Now, one more thing, or a few things, I should say. So first of all, one of your basic objects in linear algebra was a linear transformation. So linear transformation from Rn to Rn, right? If we were talking about finite dimensional vector spaces, say V to W, right? So maybe I should write this as Rn and Rm, right? If these are finite dimensional. So in the finite dimensional case, of course, we start out with, say, a linear transformation we call T, right? And how did we find it? How did we define this linear transformation T? It was, so T is linear transformation if the following was true, right? T of, say, U plus V was T of U plus T of V for all U and V in V. And secondly, the linear transformation applied to scalar multiplied vector was just scalar multiplication. So this is for all C in R and U in V. Okay. We could combine those together into kind of one statement, which is that T of CU plus DV is equal to CTU plus DTV. Right? This is like the key defining thing on a linear transformation. Now, here's a big, nice counterexample farming statement. Is every linear transformation a matrix transformation? The answer to that is no, in general. But if V is finite dimensional, implies any linear transformation is a matrix transformation. And so you could think of any such linear transformation as given by some matrix A, where A was called the standard matrix of T. Okay. All right. Okay. And so, let's first of all talk about having a symmetric. So let A be an n by n symmetric matrix. What does that mean? It means that A transpose is equal to A, right? What's a matrix transpose? It's the operation on a matrix where you take all of its rows and replace and swap its role to being a column instead. So the first row of A becomes the first column of A transpose. The third row of A becomes the third column of A transpose, and so on, right? And so here is two examples. Okay, and we'll do another one. Let's do okay, so this one is symmetric This one is not symmetric. It fails in a single slot, right? So this one's symmetric. This one's not symmetric. So let A sub A be an n by n. Of course, if it's going to be symmetric, it's got to be a square matrix. If A transpose is going to be equal to A, it's got to be a square matrix. Can't be possible. Otherwise, saying that A is a symmetric matrix is also saying that the associated standard matrix A is a symmetric linear transformation. What does this mean? This tells us that AX dotted with Y is equal to X dotted with AY. This is another thing we get here. Okay. All right. Quickly, another definition. A vector V is an eigenvector of, or maybe I should say, of a matrix A associated to eigenvalue lambda if A times V is equal to lambda times V. So remember, the key motivation here, or at least one quick way of thinking about it, was that an eigenvalue eigenvector pair, often called an eigenpair, right, it put you in a situation where multiplying your vector by your matrix A yielded a constant times that vector. So on such vectors, multiplication by A acts like multiplication by a scalar, right? And matrix and scalar multiplication are very different typically, but on these vectors, they act the same, and the scalar that it acts like multiplication by is called the eigenvalue associated to that eigenvector. Okay, so you can talk about eigenvalues associated to a matrix, and then there are eigenvectors always associated to some eigenvalue. You can't talk about eigenvectors floating around in the wild. They're always associated to some eigenvalue. And of course, you devoted quite a bit of time in linear algebra to discussing this sort of thing, right? To discussing eigenvectors, eigenvalues, all these things. Okay, now one of the last theorems that gets stated in Math 240, right? This is like what you do maybe in like the second to last week or something, is called the spectral theorem. But it turns out that the spectral theorem and its infinite dimensional analog is exactly what we're interested in. And it tells you that if you're dealing with a symmetric matrix, the eigenvalues are particularly nice. So let A be a symmetric matrix. Then all the eigenvalues of A are real, right? That's usually not the case. Even for a 2 by 2, sure, you can come up with some 2 by 2 matrices that have all real entries but complex eigenvalues. Then all eigenvalues are real, and there exists an orthogonal basis of Rn consisting entirely of eigenvectors of A. Now this is a special thing. An orthogonal basis that consists entirely of eigenvectors of A, this would be called an eigenbasis. So this could be cleaned up by saying an orthogonal eigenbasis associated to A exists for Rn. This is extremely nice, and so this basically tells me that not only are these orthogonal, all these eigenvectors are orthogonal, they also form a basis for Rn. They're eigenvectors of A, and this is actually like an if and only if statement. So this only happens when A is a symmetric matrix. So this is the only way that this can possibly happen. And so it turns out that if I write a generic vector x in Rn as a linear combination of such vectors that I get from the spectral theorem, well, since they're an orthogonal basis, remember this fact I said that allows me to, where did I put it? Here we go. That allows me to write my vectors linear combination of these orthogonal vectors where I know what these coefficients are. It turns out that if I write this as a linear combination of this eigenbasis, this orthogonal eigenbasis, then I can write this as the sum from I equals 1 to n of the projection of this x onto each individual eigenvector, okay, which is the sum from I equals 1 to n of x dotted with v sub I over v sub I dotted with itself times v sub I. And it turns out, and right now it might not be clear what it is that's going on here until I start rewriting some of this notation. But what it is that's actually going on here is that this is like the finite dimensional Fourier series associated with the linear transformation A. So, interesting. Now, on to the infinite dimensional case. In the infinite dimensional case, now my examples, right, are like I had before, C infinity R, so space of smooth functions on R. This is, we'll say, continuous functions on omega, right, space of continuous functions on omega, etc. Things like this. So my vectors now, they behave in the same way as vectors, but it's useful to think of them as functions since an infinite dimensional vector space, kind of the most useful examples of those are these function spaces, right? And so my vectors are functions, say f and g, right? So again, infinitely many components, you can think about it like that. Well, you might say, could I think of these as like, basically a sequence instead of a vector now that terminates after some finitely many terms? I can think of them as a sequence. Yeah, but you can think of them as a sequence. That's one interpretation here of doing this. But it's going to be more useful to think of these as just functions indexed by like my variable value, right? So as I said before, f of x is kind of like the xth component, where now that index, these are indexed by a continuous range of values, right? So there's a continuum of components. And now, what is my inner product for such spaces? What are linear transformations for such spaces? For linear transformations, this may have already been discussed in your 240 class where, some examples of linear transformations that were not matrix transformations pop out of this here. What is a linear transformation? It's an object that respects linear combinations, right? So T of a linear combination of vectors is a linear combination of vectors. That's all it does. It respects the object of linear combination. Do you know of any kind of operator, object acting on these spaces that respects linear combinations? Maybe I should phrase it a different way. Do you know of any linear operator that, or any operator, I should say, that takes a thing like this and allows you to pull scalars out of it and breaks up across sums? So here's one example, d, the derivative, and I, the integral. So here's two examples, right? Of course, if I think of d as this operator d dx applied to scalar times function plus scalar times function, hey, guess what? Oh, yeah, right? That's exactly how that behaves. What about integral of AF plus BG? Oh, yeah. Oh, yeah. Okay. So, yeah, you've been dealing with linear transformations on infinite dimensional vector spaces ever since you've been able to do calculus, right? So that's some examples of linear transformations. Of course, these aren't the only ones. There's plenty more, but here's some examples of two. And these are not, for instance, matrix transformations, right? You might pick a space that's like polynomials up to some degree, and you can interpret it as a matrix. But other than that, in general, right, on some space like this, it's not a matrix. But what about the inner product? So what is our dot product here? So what is our dot product here? Well, the inner product is, so let's define the inner product. So let f and g be in whatever infinite dimensional vector space I'm talking about. So let's let f and g be in the infinite dimensional vector space. Then we can have a vector space that is some kind of function space where f and g are in some kind of function space. I'll call it I'm going to call it v of AB. So they are functions defined on AB. And of course, we could pick a vector space that's nice, like continuous functions or smooth functions, whatever. Okay. Let's define f and g by, so this is the pairing of f and g. This is the inner product. So the inner product, you can call it a dot product if you really want to, but it's better to talk about as an inner product here. The inner product of f and g is, we write it as f paired with g here. This is the integral from a to b of f of x, g of x, dx. So they are integrated against one another from a to b. Okay. Now, this is an example of what's called the L2 inner product. Okay. There are other inner products. Taking a space and putting an inner product on it turns it into an inner product space of sorts. Depending on the various assumptions made, you can talk about what kind. There are special names for different types of these spaces. So this is an example of what's called the L2 inner product. L2 on a set is the set of, or it's the space of square integrable functions. So L2, like omega, is square integrable functions on omega. What does square integrable mean? It means that if a function is in L, it means that, like, maybe I should say over omega, that this integral is finite. Okay. So integrable functions would be L1 here, where just this integral of like the absolute value of f of x is finite, right? So we've already talked about integrable functions. This is square integrable functions. Okay. All right. And so this is what my inner product looks like. So as before, we had a vector space, right? Even in the finite dimensional case, all of those vector space axioms, none of those reference an inner product at all. None of those reference a dot product whatsoever. Okay, we had to assign the dot product on it, and now we turned our finite dimensional vector space into an inner product space, and we had notions of length, orthogonality, and all those things, right? So in a similar fashion, we have an infinite dimensional vector space. We assign an inner product in this way. This is our dot product now, and it turns our infinite dimensional vector space into an inner product space. Well, just like before. So just as for the dot product, this gives us a notion of length and angle, which really what we're interested in is orthogonality. Okay. How does it give me length? So length, what's the length of a function? So the length of a function, again, I'm going to use the double bars here. So the length of a function squared, we'll say, is defined to be the function f paired with itself. Just like, so recall, all the way back to the dot product, right? How did this give us length in the dot product case? Well, the length of a vector squared is the vector dotted with itself, the vector paired with itself. Here, that's exactly what we have here. We have our function, which is our vector here, paired with itself with respect to this inner product, which is the integral from a to b of f of x squared, right? So f squared of x, or f of x squared dx. Okay. All right. Okay. And so I have this, I could write this if you really want to. You could think about, it's usually easier, of course, to deal with this quantity squared, but this length is going to be the square root of f paired with itself. So it's the square root of the integral from a to b f of x squared dx. This is the length of our function here. Okay, thought of in this way. Okay. All right. How does it give us orthogonality? Well, for dot product, right, two vectors were orthogonal if and only if their dot product was 0. So here, f and g are orthogonal if and only if their inner product is 0, i.e., when you integrate them against one another on the interval a to b, you get 0. Now, if f and g are nice enough, then I can make statements like, oh, what is an example of a function like this that is orthogonal to every other function? Well, it has to be 0, right? If f and g can be like nastier functions, then those, I can't quite say that. Technically, I have to throw in some stuff about, it could be 0 off a set of measure 0 or something. But I'm not going to get into any of that stuff. Just know that for nice functions, a function that's orthogonal to every other function is going to have to be 0 here. Okay. And so notice, so recall, what sorts of things have you seen like this in this form recently? Well, on the homework, right, that is currently due. When did I say it was due? Was it due maybe Wednesday? So it's due like tomorrow or whatever. Of course, there's the orthogonality relations, right? Sine of like n pi x over L times sine of m pi x over L dx is equal to 0, right? So, of course, now, right, in terms of our inner product, this is us saying that sine of n pi x over L paired with sine of m pi x over L is 0. Okay. What about these relations like the integral from 0 to L of sine of n pi x over L squared dx is equal to, what was this? This was L over 2, right? But what is this? This, on the left, this is the length of sine of n pi x over L squared, right? This is our L2 length. Right, I'm talking about this whole quantity, of course. This is like our L2 length, right? Our L2 norm. Okay. So this length, in this sense, is the L2 norm. Okay. Of course, this also gives us a way of thinking about angles and projections. So what about the projection of a function f onto a function g? Well, I can define that in the exact same way. It's the inner product of f with g divided by the length of g squared times g. Okay. Remember this form, right? Remember this formula. Okay. And so, just like before, we had linear transformations, which were modeled as matrices, right? Matrices of some size. Okay. This is in the finite dimensional case. In the infinite dimensional case, these linear transformations that I've already given examples of, right? So the derivative is one, the integral is another. we're going to call them linear operators. So differentiation, integration, and others. So here's one. I'm going to call it script A, and it is minus d squared dx squared. You'll see the reason for the minus here in a little bit. So this is a linear operator that is minus the second derivative. Okay. Okay. This is an example of a linear operator. Of course, the second derivative is a linear operator for the same reason the derivative is a linear operator. So this is a linear operator. And we're going to talk about this in the context of functions defined on a closed interval, right? And so let our vector space V be, we'll say C2 functions on the closed interval a to b. Okay, so they are continuously twice differentiable on the closed interval a to b. We define script a to be the linear operator that is minus the second derivative. So this is a linear operator. And we'll say in addition that f here, say such functions satisfy a certain boundary condition at x equals a and x equals b. So if you like, this is like C2AB with function satisfying some certain boundary condition. And this is a special class of functions taken together. And we define A to be a linear operator on this space V. Okay. Of course, you can check that it's a linear operator, right? Check for yourself that if I apply this to functions, so we would say like a function is in V, right? If so x1, x2 are now functions in V, and I'll use capital letters just so that you don't get confused. But remember, in our infinite dimensional vector space, our vectors are functions here. So then on this space V, let's apply this operator A to a linear combination of functions now. And you can just check for yourself that indeed this is C1 script A x1 plus C2 script A x2. So indeed, this is going to be a linear operator. Okay. Now, this minus sign is going to come to us for the same reason that it's useful in many cases to put a minus sign on the Laplacian. We'll see that in a bit. Okay, and so what is it that I'm doing here, right? So, what is the idea? So, step one, treat the script A in an analogous way to linear transformation A, right, in the finite dimensional case, and we'll say this is a square matrix. 2, show that script A is symmetric in some sense. 3, use this to say via a spectral theorem something about eigenvectors and eigenvalues for script A. Right. And this spectral theorem, so this spectral theorem then gives us a nice orthogonal eigenbasis associated to the symmetric operator script A. This is what we want to do. And, you know, I could kind of hold it in and not let you know, but what type of nice orthogonal eigenbasis am I going to get? So first of all, these eigenvectors are not eigenvectors, right? I mean, they are, but they are eigenfunctions. Because our vectors are functions here. These lead to eigenfunctions here. This spectral theorem in the infinite dimensional case gives us nice orthogonal eigenbasis. What do you think this nice orthogonal eigenbasis is going to be? It's these. It's those. That's what it gives us. All right, it gives us those. So those are going to be the associated eigenfunctions, which are playing the role of eigenvectors for the symmetric operator A. And it turns out miraculously that these fill out my solution space that I'm interested in. And so with some very mild assumptions, all of these facts about linear algebra carry through, and I can write all of this stuff as, you know, all these things I want to write as linear combination of these things, I can do so because of this. Okay, and so what is it that I want to look at, right? So let's look at the eigen. It says that I want to consider this script A. I want to show it's symmetric in some sense. Okay, I'll talk about that later. I want to discuss eigenvectors and eigenvalues for script A. So what would the associated eigenvector definition be for script A? So let's recall when we had an eigenvector corresponding to some eigenvalue, it was AV is equal to lambda V. So then an eigenfunction for script A would satisfy script A times applied to my function x is equal to lambda x for some eigenvalue lambda. But what does this mean? What does this mean? Remember, script A I defined to be this thing, right? Script A is minus the second derivative. So this is saying that minus x double prime is equal to lambda x, or that x double prime plus lambda x is equal to 0. This is an ODE, right? And then you ask yourself the question, do I know of any functions whose second derivatives are equal to like some constant times itself, right? Do I know any functions like that? Yeah, of course I do, right? Of course I know some functions like that. You might be looking at them somewhere on this page, right? There's a couple of them. You might say, are those the only ones? Well, let's think about it, right? But here's at least a couple of examples of things that satisfy this property. Its second derivative is equal to some constant times itself. Okay. Now, a solution to this would be called an eigenfunction corresponding to some eigenvalue, lambda. So just like we talked about eigenvectors and eigenvalues, we're going to talk about eigenfunctions and their associated eigenvalues. Okay. Well, it turns out that to figure out what the eigenfunctions are, this assumption that these things satisfy a certain boundary condition comes into play. In fact, the boundary conditions, in a way, determine the eigenfunctions. So it turns out these boundary conditions determine the eigenfunctions in some way. And so here's 3 examples of types of BCs. These are the most important 3. And then there's one more we'll talk about. So there's Dirichlet boundary condition, which is what? So in each case, we have a function defined on AB, right? So x of x defined on AB with x of A equal to 0 equal to x of B, right? So these would be homogeneous Dirichlet boundary conditions. Okay, so that's 1. Here's 2. Neumann boundary condition. So again, x of x defined on the interval AB. Neumann condition would be x prime of A is equal to 0 is equal to x prime of B. And thirdly, we have periodic boundary conditions. So again, x of x defined on AB, and we have the conditions that x of A is equal to x of B, and x prime of A is equal to x prime of B. There are also mixed boundary conditions. We'll talk about those a little bit later, which is, like at one end you have a Dirichlet condition, the other end you have a Neumann condition. Something like that. Okay. And so, here is the point. For a wide class of boundary conditions, but specifically for the 3 above, for these boundary conditions, eigenfunctions corresponding to different eigenvalues are orthogonal to each other. Thus, we have the consequence of the spectral theorem right here, which suggests us in some way that we can interpret this script A operator as being symmetric in some way. Okay. All right. And so the way of kind of seeing this is as follows. If we wanted to see how, remember, the x that we seek, right, satisfies this. This is the eigenfunction eigenvalue relation, right? And so we can actually immediately prove that this is the case in the following way. So So quick proof. Note that minus x1 double prime times x2 plus x1 x2 double prime can be thought of as the derivative with respect to x of minus x1 prime x2 plus x1 x2 prime. Okay, you can check that yourself if you like. Now let's integrate both sides. So then the integral of minus x1 double prime x2 plus x1 x2 double prime, this integral, right, with respect to x, we'll say, is integrating this, of course, and using fundamental theorem of calculus here. I'm integrating the derivative of this thing from a to b, so fundamental theorem of calculus tells me this is minus x1 prime b x2 b plus x1 b x2 prime b minus x1 prime a x2 of a plus x1 of a x2 prime of a. Okay. And so this is going to be true for every x1, x2 that are, say, smooth on the interval a to b. And the question is, we want this right-hand side, to be equal to 0. And it does for a huge class of boundary conditions, but specifically for our three boundary conditions. So for our three BCs, you can just check that this expression is equal to 0 for all three of these, which motivates the following definition, right, where I could just define boundary conditions that make this vanish to be symmetric boundary conditions. So definition, any BCs that cause the right-hand side above to vanish are called symmetric BCs. For this problem. Okay. And so that is x1, x2 both satisfy the BC in question. So if x1 and x2, two functions satisfying the boundary condition in question, if they satisfy the relation that this right-hand side is equal to 0, those are called symmetric BCs. And so if that is the case, so for symmetric BCs, what we have is that this integral is equal to 0. So this integral is equal to 0, which another way of saying that is that the integral from a to b of, right, this integral is always over a to b. It didn't really matter here before. Here. Okay. Right, so that we're being sensible. So this is the integral from a to b minus x1 double prime x2 dx is equal to, I'm just moving one of these to the other side, the integral from a to b of, I'm going to write this as x1 times minus x2 double prime dx. And the whole reason for this is so that I can rewrite this as the following. This is just the differential operator script a applied to x1 paired with x2 in the L2 inner product is equal to x1 paired with script a applied to x2. And now you see why we included the minus sign on script a, because if we didn't, then we'd have the minus sign showing up here. Notice this is exactly the expression that I had here for a symmetric matrix, right? AX dotted with Y. If I rewrite the dot product as an inner product, parentheses, this would be AXY is equal to XAY. Oh, that's exactly what I have here. Okay. And so this script A, is a symmetric operator in this sense. Okay. And now to show that for different eigenfunctions associated to different eigenvalues are orthogonal, what does this mean? Well, let's say that we have like script A x1 is equal to like lambda 1 x1, and script A x2 is equal to lambda 2 x2, right? They satisfy some boundary conditions here. Well, script A applied to x1 is just x1 double prime is equal to, or sorry, minus x1 double prime is equal to lambda 1 x1, and this is minus x2 double prime is equal to lambda 2 x2, right? And then what do I do here? Well, I say, okay, now if I were to say compute this integral from a to b of minus x1 double prime x2 plus x1 x2 double prime dx, this is equal to 0 by our computations from before for symmetric boundary conditions, right? That is equal to 0. And so now what? Well, by these relations, replacing these terms with the eigenvalue terms, this would be the integral from a to b of lambda 1 x1 times x2 plus lambda. So let's see. Oh, this would be a minus because this is minus x2 double prime. So this would be minus x1 times lambda 2 x2 dx. And so this would actually be lambda 1 minus lambda 2 times the integral from a to b of x1 x2 dx. So if lambda 1 is not equal to lambda 2, so if these are two distinct eigenvalues up here, then this expression is not 0. So the integral from a to b of x1 times x2 dx is equal to 0, but that's exactly saying that the inner product of x1 and x2 is 0, i.e. x1 and x2 are orthogonal. So we have absolutely everything that we talked about in the finite dimensional linear algebra case carrying through to our infinite dimensional case. And this is going to mean that solving this differential equation, right? So solving my differential equation that looks like this, right? i.e. solving the equation x double prime plus lambda x equals 0. This is called an eigenvalue problem. And the solutions are eigenfunctions. of this operator script A. Sorry, this shouldn't be a minus here. So solutions are eigenfunctions of script A, and it turns out these eigenfunctions fill out the space in question we're interested in. Okay, so in order to see that, we'll have to wait till the next lecture. So next lecture, we're going to see exactly how this relates to all of these things. We're going to compute these eigenfunctions for the boundary conditions in question, and finally, we are going to get to why we're doing this, what this matters, like why this matters at all. My my first kind of hint here, if u of xt solves, say, let's do u sub t is equal to, like, we'll say like u sub xx, and if furthermore we impose a condition that u of xt can actually be written as a product of functions x and t, where x is a function of x and t is a function of t, so that u is a function of x and t, but really it's just a product of two functions that are individually just functions of x and t respectively, then when I compute u sub t, of course, that is just x of x and t prime of t, and u sub xx is going to be x double prime of x t of t. And so, for instance, this equation could be written, right, this is u sub t minus u sub xx equals 0, but in terms of these x's and t's, this would become x double prime of x minus, so this would be, this would be x of x t prime of t minus x double prime of x t of t, and that's equal to 0. Well, can we see yet what's going on here? Maybe it's not totally clear. Right, so think about this for a second. Think about how an expression like this could arise out of this consideration. This is funky step I've done here. What is it that I'm doing there? Well, we'll see next time. Okay, so we'll see in tomorrow's lecture exactly where all this is headed. So anyway, that's it for today. I'll see you all tomorrow.